let's look at a second thing where I put some lone pairs on there. Anytime I toss some lone pairs on something like this, I'm just making this structure up, but just so you can see it. If there's lone pairs on there's not a third chlorine on the trigonal planar structure, it becomes bent. That immediately becomes polar. So anytime you put some lone pairs on a trigonal planar, that happens. Anytime you put lone pairs on a structure like this, then it becomes polar. Whether it's that or something like that, it's polar. Okay, it becomes bent. And you can't really have a carbon structure with lone pairs, but just for illustration purposes. Now, in this case with this phosphorus, if that becomes a lone pair there or a seesaw shape, that becomes polar. Even if it becomes T-shaped with two lone pairs on the phosphorus, it's still polar. Even if this was a chlorine, it doesn't matter, it's still polar. But if it gets that third lone pair, then it becomes linear, opposite sides are the same. This is non-polar. Same kind of thing will go down here. If I have a square pyramidal type structure with one lone pair, that's polar. But if I put the second one on here like that, that becomes non-polar because now both axes or lines are equal. If I change this up a little bit and put a fluorine here, that's polar because opposite sides don't match. Likewise, this would be polar because opposite sides don't match. But if I erase this and change this around to put the fluorine here and the chlorine here for this square planar structure, now I've got the fluorines opposite to each other and the chlorines opposite to each other. So now this would become non-polar. Again, I'm making all these structures up just for illustrative purposes, putting the lone pairs where probably the Lewis structure wouldn't allow it to go, but just want to illustrate how the polarity of different molecules would work in different examples.